Greetings, it's Paul with a script that's designed to show you how to do various forms of integration in R and then how to use the excellent built-in numerical integration functions that R supplies. Let's start with Darboux integrals. The unique feature of Darboux integrals is that they allow you to use arbitrary partitions. So let's set one of these up in R. I'm going to be integrating from 1.5 to 2.8. I picked a function that has some nice wiggles in it, and notice that when you do integration or plotting, what you want is a function that's a function of x only. So I define the function of x for which the formula is x plus sine 10x over 2, and then the plot function gives us a nice graph of that function. Now what I'm going to do is generate a partition of the interval from a to b, and the way I'm going to do that is to ask R to draw 8 samples from a uniform distribution in the interval from a to b. And you see down at the bottom the samples that were generated. The problem is they're not in ascending order, but I can fix that with the sort function. And now we've got them in order. I can set up an axis where the subdivision points in the vector capital P are indicated by little red marks. And then I can call the very useful function AB line. When I say V equals, it's going to draw me a vertical line in the chosen color, in this case red. And presto, we've got the interval from A to B divided up, and we can now proceed to do a Darboux integral. Now the nasty thing about Darboux integrals from a practical point of view is that in forming the Darboux sum, you need to find the minimum and maximum value on each of these intervals. Fortunately, R has a function that will do this for us. It's called optimize, and it gives you back two things: $minimum, one item in the list, is the minimum. That's the location at which the minimum value is achieved. And then the actual smallest value is given by $objective. So there I have shown a vertical line at the minimum. That is indeed the minimum on the second of these 8 subdivisions between P2 and P3. And you can also see I've got a green line at the minimum value. I can do the same thing to get the maximum. And I've shown that in blue, the maximum is actually achieved at the left endpoint. So now I can calculate the lower Darboux sum. Here's a function that does the job. Let's look at how it does it. It initializes a variable to 0 that's going to hold the sum, and then it runs through the partition, and for each subdivision in the partition, it takes the difference between the two subdivision points, the length, times the value of the function optimize, which defaults to minimizing, and it takes the objective. That's the lowest value, the infimum. Okay, there's the correct value for the integral obtained by the integrate function in R. Here's my lower Darboux sum. Not surprisingly, is too small, and it's quite a bit too small. This is not a good way of doing numerical integration. But now I can illustrate an interesting point about lower Darboux sums. Here's a new subdivision, a new partition with 5 subdivision points. I put them in order, and I'll show them in a different color, magenta, on my axis. And now when I ask for the lower Darboux sum for partition Q, I'll get another value that's too small. Sometimes when I run this, it's less than the value when I had more subdivision points. Sometimes it's bigger. Just having lots of subdivision points does not necessarily guarantee you're getting closer and closer to the correct value. But, and this is the key theorem about Darboux integrals, if I take the union of the two partitions using all the subdivision points, that gives me a value 2.57. That's larger than what I got for the lower Darboux sum for either P or Q. I can do the upper Darboux sum in exactly the same way. The only change is I set maximum equals true in the optimized function to get a maximum rather than a minimum. Reminder, there's the correct value. Here are the upper sums for P and for Q. And remarkably, the one with P, although it had more subdivision points, overshot by significantly more. But if I use the combined partition, then I get a value that is closer to the correct value than either the one for P or for Q. If I use a lot of subdivisions, I wouldn't want to do this by hand, I actually get a reasonable estimate. So here I've generated 800 subdivision points, sort them, put them in order. There's the correct value. The lower Darboux sum is about 0.1 too small. The upper Darboux sum is about 0.12 large. This is great theory. It's a lousy way to do numerical integration. Let's try with Riemann integrals now. For Riemann integrals, we use equal subdivisions, and R is happy to produce those with the SEQ for sequence function. I want a sequence of points that go from A to B, and I want 3 of them. That's what length.out does. So there's my sequence, left endpoint, the middle, and the right endpoint. To get a left Riemann sum, all I have to do is add up the values where I use the length of the partition times the value of the function at the left endpoint, the ith partition point. For the right Riemann sum, I evaluate at partition sub I plus 1, the right endpoint. For a trapezoid Riemann sum, what I do is average together the values I used in the left and right sum. And for the midpoint Riemann sum, I evaluate right at the middle. I add on B minus A divided by twice the number of subdivisions to go right in the middle. To get a Simpson's rule sum, I use a weight of 4 on the midpoint and weights of 1 on the 2 endpoints, divide the whole business by 6. So let's see how these do. There's the correct value of the integral. Here's the left Riemann sum. It's significantly too small in this case. The right Riemann sum is significantly too large. That's happening because on the average this function is increasing. The trapezoid sum, of course, gives me the numerical average of those two, and it's done remarkably well. It's got 2.803 when the correct answer is 2.805. The midpoint Riemann sum is even better. It gets the 5 correct, and the Simpson Riemann sum is phenomenally good. You can see the error is only in the 5th decimal place. That in spite of the fact that I was only using a single subdivision to do these. Now let's have a look at the gamma function. There is a plot of the gamma function from a small positive value up through a value that's a little bit larger than 4. And let's draw vertical lines at all the points that are either half integers or integers, because those are the values where we actually have a formula that works for the gamma function. We can express it in terms of factorials for 1, 2, 3, and 4, and we can express it in terms of the square root of pi at the half integer values. For integer values, gamma of n is just n minus 1 factorial, and I can still illustrate that by first drawing horizontal lines at the value of 0 factorial, which is 1, 1 factorial, 2 factorial, and 3 factorial. Remember, 3 factorial is gamma of 4. For half integers, there's a proof in the lecture that gamma evaluated a half integer is the square root of pi times a rational number. So what I do is take the square root of pi. That's exactly right for gamma of 1/2. Then I have to multiply by a half times 3 halves, by a half times 3 halves times 5 halves. I will show those in green. And if you look, you will see that we have indeed got the correct value for gamma of a half, for gamma of 3 halves, for gamma of 5 halves, and for gamma of 7 halves. You may recall that R chokes if you ask it to evaluate an infinite sum. What you've got to do is ask it to sum up to 100 or something like that. Otherwise, it says, you're asking me to create a vector that's too long. But the numerical integration functions in R are quite sophisticated about dealing with improper integrals. And in fact, you do better specifying an upper limit of infinity, capital INF, than giving some outrageously large upper limit of integration. Here's an attempt to write something that calculates the gamma function on my own. I have defined a function. It is a function of both x and the parameter r. So what I integrate is x raised to the r minus 1 power times the exponential of minus x, but that integral itself is just a function of r, the exponent in x to the r minus 1. Let's see if it works. My gamma of 3, that should be 2 factorial, and it came out 2. My gamma of 1/2, that's supposed to be the square root of pi. It comes out to be exactly the square root of pi. In lecture, I showed you one more improper integral, the one that shows up in the theory of Fresnel diffraction in physics. And this is an example of an improper integral that converges only because the integrand is alternately positive and negative. It's easy to show that when you evaluate the integral, you are in effect summing an alternating series. What's not obvious is how painfully slowly this series converges. So here's the function we're integrating. The function is sine of x squared. Keeps going up to plus 1 and down to minus 1, but the wiggles get narrower and narrower. And if I ask R to integrate this, it says it's probably divergent. In fact, it's not divergent, but it's only conditionally convergent. If I ask R to integrate this from 0 up to respectively square root of 1, square root of 2, square root of 3, so we're integrating up to the end of every bump in the function, and I print the values out, you can see the values are alternately too large, too small, too large, too small. That's what we expected. That's how we convince ourselves that this is going to converge. But you see, even when I go all the way to the square root of 100, the maximum value after it's been positive for a while is considerably larger than the negative value. This is an extremely slowly convergent sequence. Finally, let me show you how to use the integration function in R to check that certain density functions are normalized and to evaluate their expectations. We will start with the exponential function, and the density function is dexp. I've given a second parameter of 2, and that should give me something where the density function is proportional to e to the minus 2x. I'll plot it from 0 to 4, and you can see it is indeed dropping off exponentially. If I ask R to integrate this to infinity, I can do it, but because of this second parameter, the only way I can figure out how to do this is to define a new function that has only one argument, f. So I say the function I want is dxp for the given x and the fixed value 2. When I integrate that from 0 to infinity, I get the value 1. If I ask for its expectation, I get the value 1/2. That's correct. The exponential function with a certain rate parameter lambda has an expectation of 1 over lambda. We can do the same thing with the standard normal distribution. If I ask for d norm of x with no additional parameters, that's asking for a normal distribution with an expectation of 0 and a variance of 1. Here's a plot of that function from -4 to 4. Here is my own function f, defined to be a function of f only. I can feed that to integrate and say, integrate it from -infinity to infinity, and it comes out to 1. We proved that in lecture. And if I ask for the expectation, well, you can argue on the basis of symmetry that this is going to come out to 0, but sure enough, when I integrate it, I get the value 0. Let's do one last one. A gamma distribution with a rate parameter of 3, no, a scale parameter of 3, I guess that's called, and a rate parameter of 2. So this is the gamma distribution where the density function behaves like x to the 3 minus 1 near the origin and falls off like e to the minus 2x. Best seen with the picture. See, it's kind of quadratic near the origin, and then it falls off. Anytime you have something where it looks like a polynomial is a good approximation near 0, and exponential fall off is what you have at the end, the gamma function is a good candidate to model that distribution. So here again is my function of x only. I use the d gamma function, but say f is the d gamma function evaluated at x for these fixed values of the parameters 3 and 2. Integrate from 0 to infinity. That had better be 1 because it's a density function, and indeed it is. It's not hard to do the integral yourself and discover that the expected value should be r over lambda. Alternatively, I can ask R to do this calculation for me. I multiply the density function by x to get my f this time. I integrate, and I get, what do you know, 1.5. That's 3 over 2. Now for the mysterious chi-squared function. We've been doing chi-squared tests for a couple of weeks now, but I haven't shown you the actual chi-squared distribution because we didn't have continuous distribution functions at our disposal until this week. In fact, we just barely got to them. So here is the density function for the chi-squared distribution with 4 degrees of freedom. You say, haven't I seen that before recently? Yes, indeed you have. Let me plot the gamma distribution with 4 over 2, or 2 as its second parameter, and a rate parameter of 1/2. I'll plot that in red, and add equals true means I will add this to the existing plot. That's how I show that two functions are actually the same. The red graph overwrote the black graph, showing that the two graphs are the same. If I integrate this one from 0 to infinity, of course, I get 1. And if I calculate the expectation of this chi-squared distribution with 4 degrees of freedom, I get the same answer as for a gamma distribution, namely it came out to 4. And what's the 4? It is r over lambda. 2 divided by 1/2 is 4. What about chi-squared with only 1 degree of freedom? Woo, this one's nasty. It blows up at the origin, and it goes to infinity. It doesn't have bounded support. It's not a bounded function. The same phenomenon occurs, of course, if I take half the number of degrees of freedom and use a rate parameter of 1/2. There's the gamma function, the gamma distribution for a parameter of 1/2. It's the same function. So I will define a function f that I can pass to integrate. Now this is a challenge for R's numerical integration routines. This is no Riemann integral. This integral is improper because the function blows up here. It is improper because the upper limit of integration is not finite. But we got the right answer. It's 1. For the gamma version of this function, we know the expectation formula is r over lambda, and you can see here both r and lambda are equal to 1. So no surprise, I integrate and I get an expectation of 1. Well, YouTube is going to tell me this video may be too long to upload, but so far it hasn't let me down.